eigenvalue. A plus lambda is a plus bi, and a is positive. The equilibrium point at the origin is called a spiral source. No, it's got to have spiral. Yeah. Yeah, because we talked about source, sink, and saddle with when we dealt with real eigenvalues. So it's a different kind of source. You got to say spiral. Okay, e to the I pi, or e to the pi I. We can use Euler's formula. Remember that from like pre-calc? It says that e to the I theta, in general, e to the I theta is equal to cosine theta plus I sine theta. From what I understand, engineers use this formula a lot. Is that true? No? Okay. So anyways, if I replace that theta with a pi, e to the I pi, this becomes cosine pi plus I sine pi. What's the cosine of pi? No, -1. And then this is I times the sine of pi, which is 0. So this just comes out to -1. And if lambda is strictly imaginary, there's no real part in the complex solution, it's just plain old BI, then the equilibrium point at the origin is called a what? Center. It's the center because all the solution curves in the xy plane are circles. Okay, so today we've spent a couple of days talking about straight line solutions and finding eigenvalues and eigenvectors that help you find straight line solutions. But I carefully chose all of the examples that we've been doing up to today to make sure that when you do the eigenvalue calculation, the determinant of a minus lambda I equals 0, and you solve for lambda, you always got 2 real solutions, right? Because you always end up solving a quadratic. But when you solve a quadratic, sometimes you can get complex solutions. So that's what we're going to talk about today. So here's a system. Its vector field appears to not contain any straight line solutions. They all seem to be swirling, no straight lines. So with no other tools in our belts, we're just going to go ahead and find the eigenvalues and the eigenvectors and just do the exact same analysis that we've been doing before, even though it's going to turn out that our eigenvalues come out as complex. They're going to have some imaginary numbers in there. Okay, so to find eigenvalues, remember we do the determinant of a minus lambda I and set it equal to 0. And that is going to be the determinant of, scroll up so you can see a. This is a. And I'm going to subtract lambda I. So that would be -2, -3, 3, -2, minus lambda I is lambda 0, 0, lambda. So we end up with -2 minus lambda, -3, 3, and -2 minus lambda. Right? Okay. So I'm going to take the determinant of that thing and set it equal to 0. So I'm taking the determinant of -2 minus lambda, -3, 3, -2 minus lambda equals 0. And the determinant, remember, you just do AD minus BC. This product minus this product. So I've got -2 minus lambda times -2 minus lambda minus -9. So then how do we solve that? FOIL it out, combine your like terms. Yep. Okay, so when I FOIL this out, I'm going to get 4 plus 4 lambda plus lambda squared plus 9 equals 0. Combine like terms, and I have lambda squared plus 4 lambda plus 13 equals 0. So it's a quadratic equation. I want to solve for lambda, so I use the quadratic formula. Lambda is going to be negative b, so that would be negative 4 plus or minus the square root of b squared minus 4 times a times c, all over 2a. So this comes out to negative 4 plus or minus the square root of negative 36 over 2. And that negative under the radical, the way we deal with that, you probably learned a long time ago if you haven't used it in a while. How do you deal with a negative under a radical? The letter I. Yeah, you can pull out that negative and it becomes the imaginary number I. So lambda is actually going to be negative 4 plus or minus the square root of 36 is 6, so this is 6i over 2. And then you can divide that 2 into both the real and imaginary parts of the numerator, and you get negative 2 plus or minus 3i. Either one. You can choose either one. Yep. Yeah. Okay, so there's our eigenvalues. And then usually what we do at this point is we try to find eigenvectors that are associated with the eigenvalues. So let's pick one of our eigenvalues, negative 2 plus 3i. I'm going to have to go onto another page here. Okay. And I want to find the eigenvectors. Okay, so to find the eigenvector, I have to solve a v equals lambda v. Right, and A is the matrix negative 2, negative 3, 3, negative 2, same A from before. V is the vector xy. Lambda is negative 2 plus 3i. Yeah, sorry. Xy. Okay, so the way we did this before, this was just a nice number. That was like a 4, right? And you just distributed it to the x and to the y. And then you just have to solve the system of equations that's resulting here. So my system says negative 2x minus 3y has to equal my eigenvector times x. And then my other equation is that 3x minus 2y has to equal negative 2 plus 3i times y. Does everybody see where those come from? So I did the matrix multiplication, took this negative 2 and the negative 3, the first row of the matrix, dot product with xy. That gave me the negative 2x minus 3y. And then negative 2 plus 3i is just a scalar, so you just multiply it by both the top and the bottom of your vector. And so my first component equals the first component, and second component equals second component. On the plus 3i, so the eigenvalues were negative 2 plus or minus 3i, and I just picked one to start with. All right, so if I'm going to solve this thing, I'm going to have negative, do another color. Negative 2x minus 3y is negative 2x plus 3ix. The negative 2x cancels, right? Add 2x to both sides and they go away. And then negative 3y has to equal 3ix. The 3's cancel. So y is negative ix. So there's a restriction. I could use that equation to come up with an eigenvector. Let's see what happens when I use the other one. 3x minus 2y equals negative 2y plus 3iy. The two y's cancel. And I get 3x equals 3iy. The 3's cancel. And I get x equals iy. Another equation. Or y equals x over I. Yeah, so usually these two things come out to be equivalent, right? That's what's been happening. Either one of the equations it tells you nothing, right? Or both equations tell you the exact same thing. So it actually turns out that those two equations are equivalent. It's just a weird thing with imaginary numbers. So let me look. I've got y equals negative ix. I need to show that that's the same thing as y equals x over I. So if I take x over I, and I multiply the top and bottom of this fraction by I get xi over I squared. And what is I squared? Think back, -1. So this is xi over -1, which is negative xi, which is what I had up here. So those two things are actually, oops, why did I write that? Those two things are actually the same. All right, so given y equals negative ix, give me one eigenvector that's on this line. One negative I, yep. I'm just going to use I1 because that's what I wrote in my notes. Okay. If you put an I into this equation for x, you get negative I squared, which is positive 1. Okay, so there is an eigenvector. Yeah, I'm not quite done yet. Right, so what do we typically do? Once you have the eigenvalue and the eigenvector, you can write a particular solution, right, that looks like e to the lambda t b. Okay, for each eigenvalue, eigenvector pair, you can write a solution. So in our case, this is going to be e to the -2 plus 3i t times my eigenvector, which I used I1. So there is one particular solution. And you could do this again using the other eigenvalue, but you get the idea, right? We don't have to go through the whole thing again. And it turns out that we're going to end up not having to go back to that other eigenvalue. So we just need this guy. Okay, so this is a little weird though. We've got an imaginary numbers floating around in our solution. What we really would like is real solutions, because we have to be able to plot them in the xy plane, and we've got all these imaginary numbers. How do we do that? Okay, so that's where Euler's formula comes in. E to the I theta can be simplified, cosine theta plus I sine theta. We proved that in Calc 2 using Taylor series. You remember, right? Yeah, good. Okay, so now I'm going to combine Euler's formula with just some simple laws of exponents, and we're going to come up with a rule of how to simplify e to a complex number a plus bi. All right, so I've got this guy to start with. I'm going to rewrite it using a law of exponents that says I can do e to the a times e to the bi, because when you have like bases, you would add those exponents, so I'm just kind of going in reverse. Then I'm going to apply Euler's formula to the imaginary exponent. So I've got e to the a times Euler's formula says this would be cosine b plus I sine b. And then I can just distribute my e to the a. So I have e to the a cosine b plus I e to the a sine b. And that's it. So this is what we're going to use to simplify. Whenever we have e to a complex exponent, we're going to use this to simplify it. All right, so I'm going to rewrite one of the particular solutions we found. We only found one because I told you we weren't going to go back and find the other one. So I had that y1 of t. Oh, that's just multiplication right there? Yeah. Dot product is for vectors. Those things are just scalars. So it's just regular old multiplication. Okay, so my solution was e to the -2 plus 3i t times I1. That was the solution we found. And I'm going to apply the rule that we just came up with in number 5 to the e to the part, right? So that I can apply my rule. So first I'm just going to distribute that t. So I have e to the -2t plus 3ti times I1. Okay, so now I'm going to simplify this using that formula. So this is going to become e to the -2t cosine 3t plus I e to the -2t sine 3t times the vector I1. All right, so now I'm just going to be doing some notation changes, distributing basic things, nothing fancy. So I'm going to multiply, this is one big scalar, this thing in parentheses here. I'm going to multiply it by both components in my vector. So this is going to become a big vector where I have I e to the -2t cosine 3t. And then when I multiply I times I get I squared, which is actually -1. So this becomes minus e to the -2t sine 3t. It's just multiplying this I by my whole scalar. And then I'm going to multiply 1 times the whole scalar, which won't change it. So I have e to the -2t cosine 3t plus I e to the -2t sine 3t. Okay, so now I'm going to gather, I'm just going to rearrange the order of the terms in the second component so that all of my terms that have an I in them, well, I'll do the first component actually. If it has an I in it, I want it to be the second term of the sum. So I'm just rearranging some order of the order of the addition here. So this is going to equal -e to the -2t sine 3t plus I e to the -2t cosine 3t. So this first component of my vector, I just switched the order of the addition. And then the bottom one, I'm going to keep exactly the same, e to the -2t cosine 3t plus I e to the -2t sine 3t. Okay, so now I'm going to separate this into the sum of two vectors. One vector is going to have strictly real components, right? And the other vector has strictly imaginary components. So I'm just going to break this one big vector up into the sum of two vectors. -e to the -2t sine 3t and e to the -2t cosine 3t is my first vector. That's just the real parts. Plus my second vector is just going to be the imaginary parts. I e to the -2t cosine 3t and I e to the negative 2t sine 3t. Okay, almost there. One last step. In the second vector, there's an I in both components. I'm just going to factor it out. So this is going to become plus I times e to the negative 2t cosine 3t e to the negative 2t sine 3t. And this one I'm not changing at all. Okay, so it took a little knowledge of some old algebra, but we really didn't do any high-level math here. We just were like a little creative in how we rewrote the solution. So we started out with this guy, just the e to the lambda t, e to the lambda tv. Apply Euler's formula to the e to the complex exponent. And then we just did a bunch of rearranging to try to write it as a real vector plus I times another real vector. All right, so that will take a little bit of practice, but that's the basic idea. What's the matter? Where? What cosine 3t? This, that's positive. Yep, that's positive. Okay, so the reason that it's worth going through all this effort to rewrite the solution you came up with, instead of just leaving it as e to a complex number tv, right? We rewrite it like this because, and we have this amazing fact, if a linear system has a complex solution that you can write in the form of a real solution plus I times the imaginary solution, then it turns out that it has two other, separate from this one, it has two other linearly independent, strictly real solutions. Okay. That is, if you take just this guy, that's also a solution to the system. Or if you take just this guy, just drop off the I, just take the real part, that's also a solution to the system. So they're both solutions to the system. Turns out they're linearly independent solutions to the system. So I'll ask you to go back and just check on your own at some point that that vector all by itself solves the differential equation, and this vector all by itself solves the differential equation. You can do it later. I've asked you to check a million things. I know you know how to do it. Okay, so we've got two particular linearly independent solutions. What do you do with two particular linearly independent solutions? Get the general solution. Yeah, you combine them, linear combination, get the general solution. So we are going to have y general of t is k1 times y real plus k2 times y imaginary. So in our case, we've got k1 times the real part of our solution was negative e to the negative 2t sine 3t e to the 2t negative 2t cosine 3t. That's the real part. And then I'm going to have plus k2 times the imaginary part where we just drop the I. The I is gone. That's what makes this so miraculous. Cosine 3t e to the negative 2t sine 3t. That's the general solution to the system. Yes. So general solution to the system can come from one complex eigenvalue. So you just take one complex eigenvalue, right? Find an associated eigenvector, And then you can build the general solution from the real part and the imaginary part of that one particular solution that you found. So slight adjustment, but we can still use eigenvalues and eigenvectors when the eigenvalues are complex, even though there are no straight line solutions. All right, so in our example, the vector field appeared to spiral around and towards the origin. So let's reconcile this with the formula we came up with, right? So this is the general solution that we just wrote down. So these are sinusoidal, right? This is, remember, this is x of t, y of t. So my x of t, it's a sinusoidal function. It's a sum of sines and cosines, which makes sense that it's going to spiral, right? And what's the amplitude of that sinusoidal function? The 3 has to do with the period, remember? So the 3 has to do with the period. The k's are constants, but also distribute this e to the negative 2t. And it turns out that the amplitude is being governed by an exponential decay function, right? So the amplitude, so the sines and cosines means we're going to spiral, right? They're going to cause oscillation. But then the e to the negative 2t in front, it acts like the amplitude, and that means that the spirals are going to get smaller and smaller and smaller and smaller. Amplitude? Yes. Yep. So the amplitude would just be changing up and down, yeah. So I graphed the actual x of t and y of t solutions here, and you can see they do oscillate and approach 0. So it turns out both solutions, x of t and y of t, are sinusoidal because they both have sines and cosines in them. It's a sum of sines and cosines. And remember from pre-calc, the period of a sinusoidal function is 2 pi divided by the b value in front of the t. So this, in this case, is 2 pi over 3 would be the period. And then the amplitude is exponential decay, which means the amplitude is approaching 0. So the amplitude starts out, I don't know, at some initial value, and then it gets smaller and smaller and smaller. Yeah, I know. Almost done. So the general solution, again, rewritten. Okay, it's the sinusoidal aspect causes oscillations or spiral around the origin, and the fact that the amplitude is an exponential decay function causes the solutions to all approach 0. So let's think back to all the work that we did, right, to come up with this solution. What part of it, what exactly was it through our work that made that guy come out exponential decay? Where did that negative 2 come from? Euler, yeah, even before Euler's formula. When we solved for lambda, remember the lambda value was negative 2 plus or minus 3i. It's the negative 2, right? Because then we applied Euler's formula. When we did e to this thing, we ended up with e to the negative 2t, and then this thing became the sinusoidal part of the solution. So it was the fact that the real part of the complex eigenvalue was negative. That's what makes it exponential decay. Okay. Yeah, because this thing is just going to cause oscillations. Yeah, it doesn't matter if it's positive or negative. Maybe. Yeah, your K1 and K2 would be different if you chose a different eigenvalue to start with. Yeah. No, if finding a general solution, it will look the same, but if you wanted to find a particular solution, you might get different K1s and K2s. Okay, so it was the fact that when lambda equals a plus bi, the a was negative, right? That caused the exponential decay part of the solution. If a were positive, that part of the solution, the amplitude would have been exponential growth, and I would have spiraled out from the origin, right? And if that said e to the 0, right? If the a value were 0, that would be e to the 0 out front, which would be a 1, in which case I would have a strictly sinusoidal solution. It would just be a circle, going around in a circle forever and ever and ever. So here's a summary. Linear system with complex eigenvalues. When the real part of the eigenvalue is negative, you get a spiral sink. The real part is positive, you get a spiral source. If the real part is 0, you get a center. Yeah, circles, concentric circles, yep. And the direction of the spiral is most easily found by just computing a single eigenvector in the, sorry, didn't mean to say eigen, a single vector in the direction field. So we did that like a couple of weeks ago, just sketching a couple of vectors in the direction field. It was on the quiz I just gave back to you, right? So if you can come up with one and you just look at which way that arrow is pointing, then you know what direction all the solutions travel in. And the period of the spiral is always 2 pi over b, where bt is the input of the sine and the cosine terms. And the natural frequency, which is the number of cycles that a solution can make in 1 unit of time, it's just the reciprocal of the period, b over 2 pi. So they might ask you in your homework for either the period or the natural frequency. Okay, yeah, that was a bit of a long demo, but I think that you can try some out on your own now.